Hi Math 30s. This video is going to be on lesson 2 on radical functions in your workbook, page 448, and it's going to be exploring the graphs of radical functions. So essentially taking a function and putting it underneath a radical sign. I'm actually going to start with 2 examples not in the workbook. So the first example that I want to look at is it wants us to graph a radical function. What it gives us is it gives us this linear function here, and they call this linear function g of x. And they want us to sketch the graph of y is equal to the square root of g of x. So before we even start that, I'm going to show you how you could look at this original function and get the domain of the radical function. So what you want to do in order to get the domain of the radical function is you want to look at the original graph, and the original graph was g of x, that linear graph. And we want to look at the piece of the graph that is greater than or equal to 0. So I've got that right here. This is the piece of the graph that the function is greater than or equal to 0. So essentially, which piece of the graph lies above the x-axis. And the reason why we want the piece of the graph that lies above the x-axis is because you know you cannot take the square root of negative numbers. So once you have that piece of the graph, you simply have to just say what would the domain of that piece be. So it's from -1, and then this is going to go to infinity. So if I said, what is the domain of y is equal to the square root of g of x, the domain of that graph would be x is greater than or equal to -1. Okay, now let's look at how we're going to sketch the graph, the radical graph of this linear function. So the first thing that you're always going to do is you're going to mark the invariant points. On radical functions, the invariant points always occur when y is equal to 0 and y is equal to 1. So that's always going to be your first step. Mark those 2 invariant points because these are going to be points on our radical graph. From there, you're going to pick some points where your g of x was greater than or equal to 0. So some points I'm going to pick, I will pick this point right here, which is about x is 0.5, sorry, -0.5, and y is 0.5. And then I'm going to pick the point, this point here. So when x is 2, y is 3. And I'm going to pick this point here. When x is 3, y is 4. To find where the corresponding points would be on the radical graph, you simply take the square root of the y value. So it will always be the square root of the y value. So the square root of 0.5, I've got it on my calculator, and the square root of 0.5 is approximately 0.71. So the new point is going to be at the original x-coordinate, but once I square root that y value, it's going to be at 0.71. So that's just going to be just above. The square root of 3 is 1.73. So I'm going to have a point at 2, 1.73. And then the square root of 4 we know is 2. So I'm going to have a point at 3, 2. What you then do is you connect these points with a smooth curve. And that would be the graph of the radical function, which is the graph of this linear function placed under a radical sign. And if we look at the domain of this graph, the domain of the radical graph is x is greater than or equal to -1. Let's look at another example. So the same thing is happening, except we have a quadratic function, and they're calling this quadratic function f of x. Let's do what we did in the last example, and let's find the domain of the radical function. To do that, again, to find the domain of this radical function, you simply take f of x, and you look at the piece or pieces of f of x that are greater than or equal to 0. So the pieces that lie above the x-axis. On this graph, it would be this. That's the piece that lies above the x-axis. This is actually going to be the domain of the radical graph. So the domain of the radical graph is going to be x is less than or equal to -3, greater than or equal to -7. That will be the domain you'll see. Now that I've got the domain established, let's graph the radical. So remember, we always first mark your invariant points. They're going to be the points where y is equal to 0 and where y is equal to 1. Those are going to be points on my radical graph as well. And then we need other points on my original graph. And remember, you always pick points above the x-axis. So they give us points that they want me to select. So I'll select these points at -6, 3, and then this point at -5, 4, and then this point at -4, 3. Remember, when you are finding your new point on your radical graph, it is always the y coordinate that is going to be square rooted. So -6, comma, square root of 3 is 1.7, and then -5 and 4, sorry, square root of 4 is 2, and then -4 and 1.7. So if I plot those points, -6 and 1.7 would be about here. -4, -5 and 2 would be here. And -4 and 1.7 about here. And then you connect those points with a nice smooth curve. And that would be the graph of your radical function. And if you look, the domain of this function is the domain that we said it would be. It is less than -3, but greater than -7. Now I want you to go into your workbook for lesson 2, and I want you to go to page 449 in your workbook. So this is page 449. And we're going to be, again, graphing radical functions, but I'm going to teach you one more concept that I always will do from now on when graphing radicals that you'll find extremely helpful. When you're graphing radical functions, you want to have a red pen and a ruler. So always make sure you have a red pen and a ruler. You're going to write what I call the red zone. So the red zone is you want to put a horizontal line going through y is equal to 0, and you want to put a horizontal line, a red line, through y is equal to 1. So let me select this. Okay. Because remember, those were our two invariant points, right? Our invariant points occur when y is equal to 0 and when y is equal to 1. So what we have is we have a linear graph, so a linear function, and that is this thin straight line here. And then it says, okay, what would the graph of the radical function be? So they take that linear function and they put it underneath the radical sign. What I want to show you is that when you are within your red zone, so this is within the red zone, the graph of the radical function will always be above the graph of the original. So the graph of the radical is always going to be above the graph of the original in the red zone. Once we leave the red zone, the graph of the radical will always be below the graph of the original, which would be this piece. And that's the graph of your radical. So let's look at that same concept, this red zone, on this next example. So again, with your ruler, take your ruler and your red pen and draw a line going through, a horizontal line going through y is equal to 0 and y is equal to 1. The original graph is the absolute value of x. So that would be this thin graph here. What I want you to do is I want you to mark your invariant points. So the points again, when y is equal to 0 and when y is equal to 1. Those are invariant points on your graph. When you're drawing the radical graph, okay, so now we're going to draw the radical. When you are within the red zone, the radical graph is always above the original graph. So that is the piece of the radical graph. When you leave the red zone, the radical graph is going to be below the original. And let's do that for this piece of the graph. So again, within the red zone, here's my original. The radical is going to be above the original. Then, once I leave the red zone, here's my original. The graph is always going to be below. And you'll see this idea of the red zone is really going to help when you're given graphs, but you're not given equations. So I can't type in the equation of the radical function on my calculator. Just to sort of mention something, this is concavity, which is going to be something that we're going to deal with a lot in Math 31, so in calculus. This would be concave down. So radical graphs, the concavity of the graph is concave down. Let's look at class example number 1 now. So I want you to pause the video, do the same thing, take your ruler, create your red zone. First step you are always going to do is you're going to mark your invariant points. So go to your red zone and go to all the points where y is 1 and y is 0. That is not a point on the original graph. Because remember, these are also going to be points on your radical graph. Okay, so what do I do from here? We're going to now follow that rule of if you're within the red zone, so this is within the red zone, your radical graph will be above the original. And you make it a concave down curve. Over here, we're within the red zone. You're going to go above the original. And then here's the last piece where we're going to be above the original. From there, you're going to take points of the original, and remember, you're going to square root the y values. So this is actually a nice point to square root here. The x coordinate is -1 and y is 4. Well, we know that when we take the square root of 4, we get 2. So it's going to be the original x value and now 2. Same with this point here, right? It was at 0, 4. That's going to now be 0, 2. This guy will be 1, 2, and this point here will be 2, 2. So whenever you have a nice number that you could square root, you definitely want to do that. Now, because this was a horizontal line, my radical will be a horizontal line. So you get your ruler and the color that you're using for your radical function, draw yourself a horizontal line. Okay, we should probably take a couple other points. This point, the y value is at 3, and we know that the square root of 3, remember, is 1.7. So it's going to be at x is 4 and 1.7. We're going to just simply connect with a nice smooth curve as much as we can these points. Over here, again, that is 2, and the square root of 2 is 1.4. So about here. And then you just simply connect. So what this should be, it should be like a nice smooth curve that's continuing and going here. And then this should actually be, there should be more concavity in this piece, right? It should be a nice smooth curve. Then it becomes straight, and then it becomes the concave down curve again. Let's do the domain. So the original graph, this goes to infinity and to negative infinity. So the original graph is going to be XER. The range of the original graph would be y is less than or equal to 4. So in proper set builder notation, y is such that y is less than or equal to 4, comma, y belongs to the element of the reals. Now let's look at the domain of the radical function. So remember, how do we do that? We only look at the piece or pieces of the original graph above the x-axis. So that would be from -3, right? This is all above the x-axis. So it'd be from -3 to 16. So the domain of the radical graph would be x is such that x is less than or equal to 16, greater than or equal to -3, right? Because remember, that's the piece of the original that's greater than 0. It's where f of x is greater than 0. Now we want the range of my radical. So the highest point or y value on the original was 4. That was the highest y value. So that means that on my radical function, we know that the square root of 4 is 2. That is going to be my max y value on the radical. And we know that our min is 0. So we'll do that range in set builder notation. And that's what we would have. Okay, let's look at the last class example, which is class example number 2. So it gives us an original graph, and it says that the original graph is g of x. Then it says, what would the graph of the radical be? So put g of x underneath a radical sign, and they're going to call the radical graph h of x. They want the domain and range of h of x, and they say to not graph it, but I do find it's easiest if you do graph. So what we'll do is we put your red zone in. So we're just approximating where the red zone would be, and there's no points within the red zone. So that means there's going to be no points above the original graph. So now we're just looking at outside of the red zone. We know that when we're outside of the red zone, our radical points are going to be below the original graph. So this point here, 0, 6, where that would be on my new graph is going to be 0, square root of 6. And the square root of 6 is 2.4. So I know that this y value is 3. So I know that that's 3. So I'll actually mark that. So I'm going to say 2.4 right about here. Okay, let's get some other points. 2, 9, we know that on the radical graph is now going to be, let me actually do this one in red. So this on the radical graph is going to be at 2, 3. So right about here. We go to this point, 6, 3. On the radical graph, it is going to be at 6 and the square root of 3. So the square root of 3 is 1.7. So I'll put it about down here. This guy would be -2, and the square root of 3 is 1.7. I'm going to get 2 other points. If this is 9, then I'm going to take this point, because the square root of 9 would be 3. So that point would be the same x value and 3. So I'm just bringing that point down, and I'm having the y value be at 3. And that's going to be the same for this point over here. It's going to be the same x value, and the y value is going to be at the square root of 9, which is 3. And that would be right there. Now you connect these points with a nice curve. And here is going to be the graph of your radical, and it would look like that. So let's do the domain and range of h of x, which is going to be my radical function. Okay, what is happening is g of x, which is my original, the entire graph of g of x was greater than 0. So sorry, I won't say equal to. The entire graph of g of x is greater than 0. There is no piece below 0. So what that means is the domain of h of x is going to be xer, right? This is the domain. That's h of x. The domain of h of x will be xer. Okay, let's figure out the range of what h of x will be. So what we want to do is you always want to look for the range. If for this case, we know it's going to have a minimum, we want to look at the min value on g of x. So what was the min value? What was the smallest value on g of x? And the smallest value on g of x were these 2 points here, these 2 minimums, and the y value was 3, right? So the smallest point is going to have a y value of 3. What that means is the min value on the radical graph, which is h of x, what that would be is going to be the square root of 3, because we know that on the radical graph it's always the square roots of the y values. So the range of h of x is going to be y is such that y is greater than or equal to the square root of 3, comma, yer. We'll do this last class example. So for this example here, same thing. They're calling this g of x, and we are going to sketch the graph of h of x, which is the radical graph of g of x. Remember, with our radicals, we only want to consider the points on the original above the x-axis. So that would be this, and that would be here. Only the points above the x-axis. Let's put our red zone in. So your red zone again, when y is equal to 0, and when y is equal to 1. So there's your red zone. When you're within the, okay, let's mark the invariant points. Sorry, that's always second. So this point here and this point, these two and these two. Within your red zone, your radical graph is going to be above the original. So it look like that, this, and this. Now we need some other points. We're outside of the red zone, so our radical graph is going to be above the original. 6, 4 is going to become on the radical 6, comma 2. And then you connect that piece there. Up here, negative 3, comma 9 is going to be now at negative 3, comma 3. And that would be your graph of your radical. So now let's do the domain and range of my radical, so of h of x. So the domain of h of x, there's 2 separate pieces. I've got to talk about the domain of this piece and the domain of this piece. So what the domain would be, it would be x is such that this piece here is x is negative 2. This piece here, we knew that x was negative 3. So it's going to be between x is going to be less than or equal to negative 2, greater than or equal to negative 3. And then we had a second piece, so I'm going to do or. I've got to state the piece of this, the domain of this piece, and that's going to be less than 8, greater than 3. And then within those 2 pieces, x belongs to the element of the reals. Okay, what would the range of h of x be? You need, in this case, it's a max value, right? I need to know what this max value is here. So the max value on the original, remember that the original was g of x. So max value of g of x was 9. What that means is the max value on square root of g of x will be the square root of 9, which is 3. This here is going to be our maximum range. So let's just write that. And it would look like the following. Y is such that y is less than or equal to 3, greater than or equal to 0. And then again, y belongs to the element of the reals. That is the lesson. Here's your homework. So 4 questions. If you're watching podcast, lesson 4.